Here we go. Last lesson of the geometrical season. It's 10.3. We're going to talk about a couple of important ideas of triangles and properties of triangles. But before we do that, so I have this picture here, and I have I have four lines. Okay? And if you had to guess what the word concurrent lines meant based off that picture, what would your guess be? Yeah, Adrian.
They intersect in one point.
There you go. That's exactly what it is. All right. So concurrent lines are when, not congruent, concurrent. When, yeah. Make sure you read the word, right? Concurrent. It's when two or more lines intersect in one point. The lines are said to be concurrent, and they all intersect right there in my 1 point. When two or more lines intersect in 1 point. Okay, the next three boxes, I'm going to give you the same setup here. We're going to talk about certain properties of triangles. I'm going to tell you how to get it, and then what's special about it. Okay, the first one that we're going to talk about is something called the in-center of a triangle, okay? And the way that you get the in-center of the triangle is by bisecting the angles. Okay, so we're going to say, how do we get it? We bisect the angles. Okay, so we're bisecting the angles. So imagine there for a moment that all my triangle is labeled, say, A, and then B, and then C. Okay, so if I were to draw angle A, and I were to bisect angle A, which we can do with constructions now, we can bisect an angle. So if I was going to bisect an angle, it would be something like that, if I was going to eyeball it. But I would use constructions. But for the sake of the lesson, I'm just going to eyeball it. Okay? There's angle B. I would bisect angle B. Here is angle C. I would bisect angle C. So therefore, what does that do for me? Well, that creates that's equal to that. That one's equal to that. And finally, that one is equal to that one. Okay? Then what we're going to do is from the vertex, if we bisect the angle, we're going to draw a line. So take your straight edge as clean as you can. So from the vertex, bisect the angle and go about the center of the triangle here. Okay? Take this here. Alright, bisect the angle.
Is this still the how to get it?
Yeah, we bisect angles. This is what we're doing. I'm drawing it now.
Oh, and they're concurrent lines.
Oh, very good. They are concurrent lines. Very good, which is why we have that. Okay, bisect this angle. Okay. And if you do it right, okay, so if you do it right, they should all meet. They should meet at a certain point, okay? And the point at which they meet, right here, okay, that is called the in-center. Okay? So how do we get it? How do we get the in-center, you guys? We bisected the angles. Okay, now, what is special about it? What's special about it? Well, yeah, it's obviously in the center, okay? But it is equal distance from all the sides of the triangle. It's equal distance from all the sides. So how do we measure from a point to a side? How do we measure that? How do we measure from a point to a side? Perpendicular. So if I go from the point to the side, measure perpendicular, I would get that right there. Do you guys agree with that? If I go to the other side, perpendicular, I get that right there. And if I go perpendicular, I get that right there. You guys see that? What have I created? If it's equal distance to all three sides, that means I could put a point at all three sides. Do you agree with that statement? And then from that, I can draw a circle inside the triangle. Mind blown. That's a great conversation. If we were going to construct this, okay, you would be given a triangle like I just gave you, right? The first thing you would do is you would bisect each angle. Okay? If you bisect each angle, all the points meet at a certain point. Therefore, they are concurrent lines. Nice job, Elijah. And the special thing about the in-center is that it is equal distance from all the sides. So the way that we measure equal distance from sides, or sorry, the way that we measure shortest distance from the sides is perpendicular. So therefore, each one of those points is on a circle. We can draw a circle on the inside of the triangle. That's why it's called the in-center. Okay, so how do we get it? We bisect the angles. What's special about it? It's equal distance from all the sides of the triangle, and you can draw a circle inside the triangle. Okay, here's the same set. We're going to talk about the circumcenter now. I have a generic any old triangle over here to the left. Let's talk about the circumcenter. What we're going to do now, instead of bisecting the angles, we are going to get perpendicular bisectors of the sides. Okay? So, again, I'm going to label my triangle. I'm going to label this A, I'm going to label this B, and I'm going to label this C. Have we learned through constructions how to find the midpoint of a segment? Yes, we did. Yes, you did. You found the midpoint of a segment. You can do a perpendicular bisector of each segment. You just put your compass more than halfway, swing up and back, go to the other vertex, swing up and back, connect the lines. That's perpendicular bisector. Review the lesson, review the video if you don't see that. But for the sake of the argument of what I'm doing now, okay, I'm going to call that the bisector for AB, that the bisector for BC, and I think that is right. 1, 2, 3, 4, 5, 6, 7, 8. Yep, perpendicular bisector for that. Okay? So then I'm going to extend those lines and I'm going to draw them all in. I'm going to do my best to use a drawing tool. You do the same thing. Okay, so perpendicular bisector. Let's move this one over just a little bit if I can. Alright, that's pretty good. Okay. Again, let's try this one. Perpendicular bisector. That's pretty close. Okay, and then perpendicular bisector using construction tools would be better, but for the sake of the lesson. And again, let's see, can I move this down just a little bit? I don't have a whole lot of control of that. Okay, but we're going to call that the best I can do. Okay, so this point right here, notice what do we have? What type of lines do we have? Concurrent lines, yes, very good. So we know that this line segment and that line segment are the same, that segment and that segment are the same, and this segment and this segment are the same. So we did perpendicular bisectors for each of the three sides. So if I label properly, perpendicular, perpendicular, and perpendicular. Okay, so what is special about it? This point is equal distance. Yep, you got it. Equal distance from all three vertices. So what does that mean? That means that, I feel like I can do this in a nice red color, so the distance from there to there is the same as the distance from there to there. That's the same as the distance from there to there. That's the same. So if all of those are the same, they create the radius of a circle, and therefore I can then connect all of these with a circle around it, like this. Okay, here we go. The orthocenter. That's our third one. Okay, the orthocenter. So far, let's figure out what have we done. Well, we've split the angles. We've bisected the angles, and that gave us a nice, neat property. We've bisected the. We found the mid segments and found the perpendicular bisectors of the sides. That gave us another property. Okay. So now, what else can we do of a triangle? Well, triangles have altitudes, don't they? Okay, so I'm going to go ahead and put in all of my vertices here. Okay, and what's the definition of an altitude? It is a line from the vertex that is perpendicular to the opposite side. So I'm going to go ahead and draw in a line from B perpendicular to the opposite side, just like that. Okay, I'm going to do the same with the other ones. Okay, so from vertex A. Let's draw. From vertex A, I'm going to go perpendicular to the opposite side, and that would be somewhere about here. You guys agree with that? Okay, good. Awesome. And then I would go from vertex C, and I would go perpendicular to the opposite side, and we have another set of concurrent lines. Okay, so they meet right here. This is called the orthocenter. And these are, how did we find these? How did we get them? Yeah, we drop an altitude from each vertex. Okay? Drop an altitude from this. So the line that contains meet at a point that contains the altitudes meet at a point called the orthocenter. Alright? What's special about it? Nothing. This is the only one. There's nothing really special about that point. It doesn't have any cool properties or nothing like that. It just happens to be what we call the orthocenter. It is the point at which all three altitudes meet. Call it the orthocenter. Okay, this one's called the centroid. So what we're going to do is we're going to construct the medians from each vertex, okay? What's the definition of a median again? Do you guys remember what the median is? From a vertex? Very good. From the vertex to the middle of the other side, right? So from the vertex to the middle of the other side. So if I'm going to go from the vertex, so from vertex E to the middle of the other side, it'd be about there, okay? So that means that that segment and that segment are congruent. So I'm going to go from vertex A to the median of the other side would be about, I don't know if I had to, right there, you guys agree? Something like that? So how would I construct that? How would I construct that? What would I need to do? I would need to do what to each of my segments of my triangle, the sides of my triangle? I'd have to bisect them, and I'd find that point and then connect it to the opposite vertex. Okay, then the last one, I'll go here, and we'll go opposite side, so right about there. And these, my lines are what? Concurrent, very good. So that means that this segment and this segment equal. So how did we get it? We drew what? All three, what are these things called here? Medians. Okay, so you draw all three medians. So that is a median. And we create wherever the points meet. This is called the centroid. The centroid. So what's special about it, right? Yeah, they all look the same, but they're not because of the way that we get them. Okay, the way that we get them is different. Yeah, we'll keep it in the present tense. Draw. How about that? Draw all three medians. Right? Where they meet is the centroid. Now, what's special about it? What's special about it is its distance. Its distance. This distance from here to here is 2/3, and this is from here to here is 1/3. Okay? So what that does is it breaks up that median into 2/3 and 1/3 for each one. So that means, so this blue segment represents 2/3. This yellow segment represents 1/3. Okay? This blue segment here represents 2/3. And this segment represents the other 1/3. This segment here represents 2/3. And then this segment over here represents the 1/3. So the centroid is 2/3 of the distance from each vertex to the midpoint of the opposite side. Alright? 2/3 and 1/3. So you need to remember, for what's special about it, you got to remember the 2/3 to 1/3 ratio. Okay? So what I mean by that, again, so that is your 2/3, that is your 1/3. So the median is, or the centroid is located at that spot that breaks up that median into 2/3 and 1/3. Cool thing about the centroid is, if we cut this triangle out and it was made out of cardboard, the balancing point, like on the tip of a pencil, would be the centroid. So you could actually balance, it's equally weighted at that point.
So it's the absolute center.
Good thing like that. Alright, that's kind of a cool little fact there for that. Okay, the in-center is where the angle bisectors meet. Circumcenter is where the perpendicular bisectors meet. Orthocenter is where the altitudes meet. Centroids are where the medians meet.